It's my great pleasure to introduce Dr. Sebastian Ellis. He's a postdoctoral researcher at SLAC, the National Accelerator Laboratory. He has degrees from the University of Manchester and Cambridge, and he received his PhD in high-energy theoretical physics from the University of Michigan. Dr. Ellis was, I don't know if you were born, but you were raised basically in the shadow of CERN and the Large Hadron Collider now, obviously built during your lifetime, but sort of born into a life of particle physics in that sense. Let's give a warm welcome to Dr. Sebastian Ellis.
Thank you, Scott, for that very kind introduction and for the very kind invitation to give a talk here. So as you can see from my title, I'm going to try and give you an idea of what it is that I do. Given that this series is called What Do Physicists Do, I figured that I would be remiss if I didn't give you the answer to what at least I do by the end of this talk. And in particular, I would like to tell you what I work on with regards to dark matter and how my approach as a theorist might be somewhat different from that of an experimentalist, let's say. So, as a theorist, a lot of the work that I do sort of looks like this. A lot of it is on the blackboard, which we have a lot of blackboards in my office, in the corridors, in a room full of blackboards, bottom of the floor to the ceiling blackboards, everything is blackboards. And if you try to replace those with whiteboards, forget it. But in any case, what we do is we write lots of equations, sometimes some diagrams, some things that some of you may recognize as being what looks like a wave equation, and towards the end I'll get on to actually what these particular equations relate to. But the question that you may have is why, right? Why do we do all this? Why are we as theorists interested in some of these questions? And so, first of all, what are these questions? Well, I would argue that they're extremely fundamental questions. The first one, which we mostly know the answer to, is what are we? And most of you will know that we are made of nuclei, which are themselves made up of protons and neutrons. When they combine with electrons, they form atoms. And we sort of know how that works, modulo some small details here and there, but at least in the general picture, we have a pretty good idea of what we are and what we are made of. But then we come to, well, how did we get here, right? So this ties in with what's known as cosmology, which I will give you an introduction to in a few slides. But I would argue that it also depends very strongly on what are the components of what we call the standard model. Which are not only the particles which make up the protons, the neutrons, and the electron, but also the forces through which we interact with the various different particles. And I'll explain in turn what each of these little diagrams correspond to, and what these various forces are, and how they play a fundamental role in how we eventually made it to where we are today. So those are the things that we sort of understand well, or at least moderately well, hence the question mark at the end of this, in particular with regards to the Higgs boson. But then there are some other questions, fundamental questions, to which we truly do not know the answers, and we are still struggling with. And some of you might think of these as rather existential questions, such as why are we here? So I will argue that dark matter is crucial to our being here. And I will hopefully convey how that works over the course of this lecture. So at least on a sort of mechanical level, we can understand why we're here, if not on a philosophical level. And the other question that you may want to know the answer to is another philosophical sounding one, which is where are we going? Which again ties in with cosmology, but on a more sort of concrete level. I'll tell you where we as theorists are going currently, and why we think that's exciting, and what we hope to achieve in the coming years. Okay, so the first question, what are we? Well, there are many answers that I could possibly give to this question, and each one would depend entirely on what angle I was coming at the question from, whether I was a chemist or, as in the case maybe a physicist. But let me give you some context of what we are in the grand scheme of things. So this is a scaleless line to which I will add some numbers. We are here, the thinkers in Rodin's masterpiece. We are the humans thinking about what we are and where we are in the universe. And our scale, our length scale, is of order a meter, right? 1 meter, 2 meters, it doesn't really matter. It's all order of magnitude. So we're sort of sitting in the middle on this scale that I've drawn here, but in reality that's not true, as you will see. If we go to larger scales, so sort of order of 10 kilometers, it's actually 27 kilometers in circumference, but order of magnitudes is what we do as theorists, so 10 to the 4 meters. The Large Hadron Collider is this yellow line that you can see here in what was my backyard growing up in Geneva in Switzerland. And this is one of the major tools that we use through the eyes of experimentalists to determine what we are made of and what are the fundamental rules of the game that we play. If we go even higher in size, if you go to 10 to the 7 meters, that's the size of the Earth. So this is 3 orders of magnitude bigger than the Large Hadron Collider, and this is sort of a scale where already it starts to become a little bit difficult for us to comprehend, right? We can see a photo of the Earth and we think, okay, that looks pretty big. But if you actually were sort of tasked with explaining what 10 to the 7 meters really is, without referring to the Earth, that's actually quite difficult. And on the way extreme length scale, we have the size of the observable universe, which we estimate at roughly 10 to the 27 meters. But like I said, this is the observable universe. So the true universe is much, much larger than that. So already going upwards in scale from us, you can see that the scales involved in our problem of trying to understand what we are immense. And the other thing we can do, of course, is go in the other direction. So if we go smaller than humans, at 10 to the minus 5 meters, that's the width of a hair. So that's sort of the smallest size that we can roughly resolve with our bare eyes. Right? We can see a hair and think, okay, I can see what length scale that is. Now, bear in mind that that's roughly as much smaller than we are as the Large Hadron Collider is bigger than we are. And we're going to go way deeper in smaller sizes. So if we go another 4 orders of magnitude down in size, we reach DNA. So that's roughly the length of a strand of DNA. And of course, this is unresolvable to human eyes. And we use very large microscopes to actually understand what DNA looks like. If we go even smaller, we have the radius of a proton, which is 10 to the minus 16 meters. So compared with our size, this is way smaller than the Earth is way bigger than us. So this is really, really incredibly small. And so you might ask, okay, well, how do you manage to resolve that that is the size? Well, actually, we can go further than 10 to the minus 16 meters. And this plays back into the Large Hadron Collider. The Large Hadron Collider actually probes length scales down to roughly 10 to the minus 20 meters. So in the world of particle physics, what we often talk about is energy scales as opposed to length scales. And in that language, smaller length scales correspond to much larger energy scales. So the Large Hadron Collider collides protons, these guys that are 10 to the minus 16 meters in width, at energies of what we call 7 TeV per beam. So for a total of 14 TeV in the center of mass. And that corresponds to resolving length scales like you would with a really, really powerful microscope of order 10 to the minus 20 meters. So that is how the Large Hadron Collider tries to understand the rules of the universe to such small length scales in the same way that you can use telescopes to understand the rules of the universe at much, much larger length scales. And now, due to quantum mechanics, we know that in the end, there is a fundamental length beyond which we can no longer resolve, because that is the point where quantum effects due to gravity start to play an important role, and that's called the Planck length, which is 10 to the minus 35 meters. So you can see that between this dash and the next dash, there is a long, well, very short distance really, that we still have yet to probe and we still have yet to understand. So that is sort of the ballpark that I'm going to be talking about today. So concretely, what are we made of? So these are the fundamental quarks of the standard model. So these are the ones that we know exist, and we have observed all of them in their various different ways. In fact, the charm quark was discovered in part at SLAC. So there's the history in the US and in California of playing a major role in deciphering what this structure was. But most of us are really just involved with these first two, the up and the down quark, because they combine to make neutrons and protons in the combinations that I've shown here. The reason being that the other ones all tend to sort of decay down into these lowest ones, which then combine in these objects, neutrons and protons. So these neutrons and protons are, as far as we know, absolutely stable, although there are experiments trying to determine just how stable they really are. And neutrons have a finite lifetime, but when they bind together in nuclei, then they can last much longer, and these nuclei are generally stable depending on the isotopic arrangements. When you then combine them with what we call leptons, so this is the electron and its heavier brothers, and the neutrino cousins, and again there's 3 copies of each, the electrons combine to form atoms, e.g. helium, that I've shown here. So this is, roughly speaking, this column is the only one that you would really care about if you just wanted to ask, well, what are we made up of? But we know experimentally that all of these other ones exist. And the way we know that is through experiment, but also through theory. We would also like to understand how it is that these things interact with each other. And that's where the forces come into play. So there's a number of different forces. The first one, which you'll all be familiar with, is the electromagnetic force, which is mediated by a particle we call the photon. So the photon is a massless particle, which is useful because that means that it doesn't have a finite range, it has an infinite range. So photons from the most distant part of the observable universe can still make it to us, in part because the photon is indeed massless. And it mediates the electromagnetic force. So this means not just visible light, but also the rest of the spectrum of light, but also magnetism. Magnetism and electricity were known back in the old days of early physicists to unify into this electromagnetic force. And so that is why light and magnetism are part of the same story. The next force that we might be interested in is the gluon, which mediates the strong nuclear force. So the strong nuclear force is what ensures that those quarks that I was telling you about on the previous slide bind into these protons and neutrons that eventually make us up. It also ensures that those protons and neutrons can bind together to combine into nuclei, something which is of course necessary for us to exist in the way that we do. And then there is the weak nuclear force, which is mediated by particles we know as the W and Z boson. Fun fact, the Z was named because they thought it was the last particle they were going to discover. Jokes on them, it was not. So this one mediates, for example, radioactive decay, and is crucial in that regard. A different but equivalent description of these forces is in terms of these diagrams. So you can think of the external legs as being particles, fundamental particles, that exchange one of these force carriers, and in so doing, feel the force of that force carrier. So here, for example, these could be electrons emitting a photon and then capturing it somewhere else. And this gives rise to the famous Maxwell's equations. As it turns out, for the strong and the weak nuclear force, you could write down analogues of Maxwell's equations, but they're not particularly useful when you try to actually solve things because, in part, in the strong nuclear force, you never actually see quarks and gluons individually. The force is actually so strong that it undergoes what we know as confinement, where as soon as you produce one, it sort of pops new ones out of the vacuum and binds itself into objects like protons, neutrons, but also these sort of odd objects called mesons, which have fewer of the quarks and gluons in them. The weak nuclear force, of course, is involved in, here for example, I've shown beta decay. And then finally, as of 2012, the last force carrier that I showed on one of the introductory slides, the Higgs boson, was discovered at the Large Hadron Collider. And the Higgs is an interesting one because the Higgs is what enables all of the particles that I've told you about so far that have a mass to have that mass. So if they have a mass, they gain it through the Higgs boson and through the interactions with the Higgs boson. And so one way of understanding this is of thinking of the Higgs field as really being that, a field. So you can imagine it sort of like a snow field. You've got Higgses everywhere, and they're basically all the snow particles. And as the particles go through that snow field, they can interact more or less with that field. And that corresponds roughly to whether they have more or less mass. So for example, a photon, which I told you a few slides ago, is massless, doesn't interact with the Higgs at all. So it just skims across the top of the Higgs snowfield and doesn't feel anything because it has zero mass. A relatively light particle, such as an electron, does interact somewhat with that Higgs snowfield, and so it gets bogged down a little bit. So you can think of this as being sort of like a skier. Right? He goes pretty fast over that snowfield. And then there are heavier particles like the up quark, which also interact somewhat weakly with the Higgs field. In fact, so weakly that we still haven't really observed exactly the coupling of the up quark to the Higgs. So the fact that I'm drawing this line here is still only theory for now, not yet experiment. Then if you have heavier particles like the W and Z bosons, which mediate the weak nuclear force, they experience a very strong interaction with that Higgs field. So they get really bogged down. That's sort of like if you were wearing snowshoes, let's say. And so it's pretty hard work to get through that Higgs field. So that corresponds to having a pretty large mass. And then finally, the heaviest particle that we know of is the extremely big brother of the up quark, known as the top quark, which interacts very strongly with the Higgs. In fact, so strongly that in theorist parlance it has an order 1 coupling. It has the biggest coupling sort of it could reasonably have without starting to trend towards a region where you wouldn't be able to do theoretical computations. So in terms of the analogies that I was making, the photon is sort of like a skier skimming across the top. These electrons and up quarks and down quarks, which are relatively light, you can imagine like a cross-country skier. The W and Z sort of like a snowshoer. And finally, the top quark is some guy in his boots trying to go through the Tahoe snow that we had this winter, basically not getting anywhere at all. Okay, so that was what we are. But then you might ask, okay, how did we get here? And as I hinted to earlier on, this has to do with what we call cosmology. So cosmology comes from two Greek words, cosmos and logia, which mean basically the study of the cosmos. And in truth, what it is it's the study of the history of the universe. And so, in fact, just before this, Scott and I were talking about how often physicists are history buffs. Well, in a sense, we have to be history buffs, because part of what we do is trying to understand the history of the whole universe. So what we know so far is, okay, there was a Big Bang, followed by a period of what we call cosmic inflation. So in this period of what we call cosmic inflation, the universe expanded extremely rapidly. So rapidly, it's just impossible to comprehend how much it expanded and how quickly. So here on this length scale, you see that between 10 to the minus 36 seconds after the creation of the universe and 10 to the minus 32 seconds, the universe expanded by e to the 60. Okay? So orders and orders of magnitude of expansion. A really, really rapid process. But once that ends and the universe is sort of heated up, you get what we call the quark-gluon plasma. So that is roughly at 10 to the minus 10 seconds, so a comparative age after cosmic inflation has ended. You have all of those particles that I was just telling you about, which are massless, just floating around. The reason why they're massless is that the Higgs has not yet undergone what we call a phase transition. So there's a phase transition that it undergoes at a certain stage, somewhere in between this point here, 10 to the minus 10 seconds, and this point here, 10 to the minus 4 seconds, from where particles go from being exactly massless to all gaining their masses through the Higgs. Once they do that, we transition to this period at 10 to the minus 4 seconds where the bound states, those protons, those neutrons, those mesons start to form out of the fundamental particles, the up quark, the down quark, and the gluons, and so on and so forth. And in this process, the electrons and the neutrinos and also the photon are still just floating about, not bound to anything just yet. After this, we get what's called Big Bang nucleosynthesis. So this is when the light nuclei going up to and including lithium are formed. So obviously hydrogen is just a proton, so that was sort of already there to start with. But you start to be able to bind protons with neutrons to form, for example, deuterium, and eventually tritium, and eventually helium, and eventually lithium. And in fact, very precise theoretical calculations go into understanding how nuclei form, which will have to do with dark matter. And so I will tell you about that in just a few slides. After this, really long after all of these processes are taking place, so all of these have taken place in the first second of the age of the universe. But 300,000 years later, the universe suddenly becomes transparent to photons. So before that, the photons were interacting with everything so frequently that they weren't able to escape that sort of mass of particles that was the early universe. But after 300,000 years, finally the universe sort of becomes transparent. There's enough free space in between particles, in between objects, that light can actually escape. And amazingly, we can actually see this sort of first light of the universe. And that is known as the cosmic microwave background, which I will explain in more detail in a few slides. After that, we start to undergo structure formation. So this is how the little anisotropies, so the differences between different points on the space, which you can kind of see on this image of the cosmic microwave background, will eventually resolve over here a gigayear into what we see today, which is galaxies, solar systems, galaxy clusters, and all of that good stuff. So this all depends also on dark matter, as I will explain likewise in a few slides. And finally, 14 gigayears after the Big Bang, we are here today in a galaxy, in a rotating arm on the edge of that galaxy, discussing how on earth did we get here in the first place. So, crucially, dark matter matters at basically every step of this process. There is not a single one of those processes, except for maybe the Big Bang, where dark matter does not play an important role or could potentially completely catastrophically destroy what we observe. And therefore that provides us a good theoretical constraint and experimental constraint on what dark matter can or cannot be. But before I get on to explaining exactly why dark matters at every one of those steps, I also want to try and motivate a little bit further why we're so interested in dark matter itself. And the way I like to think of it is that it's sort of an exploration of the unknown. So if you think of the ancients, they had these incomplete maps of the Earth. Here, this was Hecataeus and Miletus, 500 years before Christ. He put Greece in the center because he was Greek, of course. And he thought, okay, well, this is the extent of the known world, so that's all there is to it. But of course, the Greeks were avid explorers, and so they were constantly trying to expand the frontiers of their knowledge. Similarly, of crucial importance to the eventual discovery of this continent, Columbus also had an incomplete map of the world, and he wanted to discover more, understand more of what his universe, which in his case was the Earth, was made up of. Well, likewise, we're interested in exploring the unknown of what dark matter is, given that we only know a small fraction. So in that spirit, let me give you a breakdown of the energy budget of the universe. And in a few more slides, I'll explain exactly how we know what this breakdown really is. So 4% of the entire known energy in the universe is what we observe. And in fact, it's not even 4%. It's really closer to 0.5%, which we see in stars. Most of it is contained in gas, in between stars, in hydrogen and helium, there's some component in those particles that I was telling you earlier about neutrinos, only 0.5% in stars, and then 0.03% in what we call heavy elements, so things like gold, like plutonium, like uranium, all of these very heavy things which are only produced in supernovae. That makes up a tiny fraction of the already tiny fraction that is the matter that we understand. So all those particles I explained to you at the beginning of this talk, that only makes up this 4% over here. 27% of the energy budget of the universe is dark matter. So if I had showed you one of those maps on the previous slide and said, okay, this is 4% of the universe, go find the other 96, you would probably be pretty interested to know what it was. So the fact that we understand that 27% of the energy in the universe is dark matter, but that we don't know what it is infuriating, right? You really want to know, what on earth is it? And then finally, 68%, or the remaining fraction, is in what we call dark energy. So dark energy is sort of an interesting one because the name makes it sound like it's going to be maybe a particle, like we think dark matter is. But more likely than not, it's actually just sort of an intrinsic curvature of the universe. So it's actually the fact that the universe is not perfectly flat, but it has some sort of curvature to its space, which is a sort of an annoying concept to try and wrangle in your head. The fact that space which seems so flat is curved, but in the end we know that the Earth is round, so maybe it's not such a stretch to think that the universe is space-time is actually curved as well. But in any case, that 68%, we sort of roughly think we understand what it is. We don't really understand how it came to make up that exact amount, but that's a story for another time. The main story that I want to occupy you with today, which will be a long one in and of itself, is this 27%, which is what dark matter is. So, as I said a few slides earlier when I was going through the history of our universe, I told you that it played a crucial role in our existence at each of these stages. So during the cosmic inflation stage, it can play a very important role because it could have been that the dark matter was just produced by whatever did inflation. So inflation, our best guess is that it was sort of perpetrated by a particle, not too dissimilar from the Higgs boson actually, what we call a scalar particle. So it's just a particle that has a particular numerical value somewhere in space. And that particle eventually had to decay to produce all of the particles of the standard model. And so it may well be that it decayed into dark matter, and that might be the way dark matter was populated. So at this cosmic inflation stage, dark matter might have already played a role, or more precisely, at the end of the cosmic inflation stage, it may have played an important role. There are even some models where the inflaton, the particle that perpetrates inflation, is the dark matter, or is part of the dark matter. But I won't go into any more detail about that, just beyond saying it is involved at that stage. If we think that it was produced at the end of inflation, then it would have been around during this period of the quark-gluon plasma. And so if it had strong interactions with those particles, it could have screwed things up. Things would not have developed the way that they did, and so you wouldn't have then got on to the next stage where bound states form. So bound states form during what I called Big Bang nucleosynthesis, and there we do know that there is a very strong constraint on what dark matter can be, and we know that it cannot have been warm during that period. So at every stage in the evolution of the universe, there is a sort of temperature associated with the universe at that given time. So if I had wanted to, I could have rewritten this axis instead of as time as temperature. And we know that when bound states begin to form, you want dark matter to have already been cold. Because if dark matter had been warm, it would have behaved like radiation, and we wouldn't get what we observe today in terms of the ratios of the light elements that we see. So we have measured very precisely how much helium, how much hydrogen there is in the universe today, and we know that that's been roughly fixed since they were formed so long ago. And so that gives us already a handle on what dark matter could have been doing during that period. And if it had not behaved according to the rules that we observe, then we wouldn't be here to observe it. So Then we get to the cosmic microwave background, which is, like I said, when light sort of first manages to escape from this primordial soup, for lack of a better metaphor. And there we have very strong handles on what dark matter could be and what it can't be, more to the point, because if dark matter is annihilating into standard model particles during that time, it would have left an imprint on the cosmic microwave background. The various different aspects of these little differences in the temperatures would have changed relative to what we observe. And the fact that we observe them the way we do tells us, okay, we have some handle on what dark matter could have been doing at that stage. But dark matter is actually crucial in forming these differences in little temperatures here and there, and that is why it's also crucial during structure formation. If you want to, you can think of dark matter as sort of being this gravitationally interacting object, much like a galaxy would be a gravitationally interacting object when you consider it as a whole. If you put a star within the sort of gravitational well of a galaxy, it will just roll down into that well and join the galaxy. Well, dark matter sort of bends space-time into these deep gravitational wells, and it would attract things into those gravitational wells. And without those, you wouldn't get the structure formation that we observe on the scales that we observe it. So in fact, the sort of smallest galaxies that we observe, called dwarf galaxies, tell us that dark matter has a minimum mass that it cannot go below. Otherwise, those structures wouldn't exist. We would not see them. But the fact that we do tells us that dark matter has to be heavier than the scale that corresponds to those dwarfs. So dark matter matters at every step. So beyond this, what evidence is there for dark matter? Well, the earliest evidence for what we now call dark matter we owe to this gentleman, Fritz Zwicky, who was a Swiss astronomer based at Caltech for his most productive years. And he made observations of the Coma cluster, and he used something called the virial theorem, which relates to the amount of kinetic energy, so the rapidity with which particles, well, stars in this case, are moving around in this galaxy cluster, is related to the potential energy of that bound system. So in a gravitationally bound system, there is a certain potential energy associated with that, and you can relate it to the velocities of the stars via the virial theorem. And he inferred from observations of the Coma cluster that the thing was way heavier than it appeared to be. You count all the stars and you think, okay, it's got a certain mass. But then you look at the velocities and you think, no, it has to be way, way heavier. And so he said, okay, well, there has to be something called dark matter in there to explain why it's so heavy. Further, and the one that people very much like to show because it's incontrovertible, is evidence due to Vera Rubin, which we know as rotation curves of galaxies. So here you see data in the form of these points from an observation of a particular galaxy as a function of the distance away from the center of the galaxy. And the y-axis is showing you the velocity of the stars as they orbit that galaxy. And what you can see is that if you just had pure gravity as we know it, you would expect this to be the rotation curve that you would observe in that galaxy. But instead what you observe is something that sort of keeps rising and eventually flattens off. So what that tells you is that because the velocity has to be related to the mass distribution in that galaxy, there is mass in here that we cannot see, whose density is dropping off like 1 over the radius squared. And so that tells us that there is some matter that we cannot observe because it doesn't interact with light, aka dark matter, sitting in this galaxy, which makes the rotation curve follow the path that it does, as opposed to the one that you would have predicted just based on general relativity. Now at this point, you might ask, well, okay, some people say, well, what about modified gravity? I'll get to that in a couple of slides, why modified gravity cannot explain this, but be consistent with other evidence. So the next piece of evidence, which I think they would take away my theorist card on dark matter if I didn't show you, is the bullet cluster. This is the one that people very much like to show because it's a truly beautiful image. And it's also really incredible that what you can resolve from here is that in that center is where most of the regular matter is sitting, because that's the stuff that we observe, that's the stuff that's emitting light, and we can see that it is in the middle. But where we actually observe all the mass due to gravitational lensing, we see it's actually on the sides in these regions that are shaded in purple by the artist's rendition. And so, using a technique known as gravitational lensing, we infer the fact that there is more matter out in these two lobes than there is in the center. And this was a couple of galaxies that collided and went through each other. And because matter interacts with itself, it slowed down as it passed through itself. Whereas the dark matter, which interacted very weakly with both the visible matter and with itself, just passed straight through. And so that's why it's on either side. So not only is this evidence of dark matter, but it actually tells us that dark matter can't interact more strongly than a certain amount, because if it did, you wouldn't observe this separation of the matter from the dark matter from the regular matter. And finally, the cosmic microwave background, as I alluded to earlier, where this data was taken by the European Space Agency's Planck satellite, actually provides sort of the best and most robust test of dark matter itself. So what you can do with the cosmic microwave background is you see that there are various, so this is all temperature. Red is hot, blue is cold, as you might have expected. And you can see that it's not just uniform. Right? People usually tell you that the universe is homogeneous and isotropic. So homogeneous means that if I dropped you here, it would look the same as if I dropped you here, as if I dropped you here. Clearly, it isn't quite. Also, it's not isotropic. Isotropic would mean that if I plopped you at any one of those spots and you looked around in every direction, it would look the same in every direction. But clearly, it does not. If I put you on the edge of this hotspot here, it's going to look different going this way than it does looking that way. So that's what we call the anisotropy of the cosmic microwave background. And the way that we measure this is by taking two-point correlation functions. So you basically pick 2 points on the cosmic microwave background map, and you ask, are they correlated? And if so, how correlated are they? And what this gives you is this curve, which tells you on the x-axis here the angular scale. So if you looked at the plot that I showed you on the previous slide, if you took wide points on that plot, that's on the left here. If I took points very near each other, that's on the right of this plot here. And it tells you how correlated they are. And so without going into too many of the details, because they're quite involved, you will notice that there are various peaks associated with what we call the power spectrum. And these various peaks actually tell us very interesting information about the content of our universe. And this is where I got that breakdown of the matter and the energy budget of the universe data from. So this first peak tells us how curved the universe is, how much bend is there in space-time. And so that is roughly how much dark energy is there in that energy budget that I showed you earlier. And so we know, based on the size of this peak and the position of this peak, that there is a certain amount of curvature to the universe which we infer to be dark energy. And then these second and third peaks are related to how much regular matter there is. So how many quarks there are, how many protons, neutrons, electrons, neutrinos, all of the things that we have observed and that make us up. All of that information is contained mostly in this first peak, but also there's some degeneracy with the second peak. But then that third peak also tells you about what dark matter is. So the fact that these two peaks are almost the same height tells you that there's a hell of a lot of dark matter. And in fact, that's how you know that 27% of the universe is made of dark matter, is from comparing these two peaks relative to each other. So this is all experimental evidence, which is backed up, of course, by real theory, in the sense that it relates to real experimental data that we've observed. But then you may ask, okay, so why are we here? Why am I, as a theorist, up here telling you about dark matter and why we're still thinking about it and why we're so interested in it? So the first question you might ask is, well, why isn't it one of those particles that you told me about from the Standard Model 5 or 6 slides ago? Right? You had all of this zoo of particles to choose from. Surely one of them should have satisfied the conditions required of it to make up the dark matter. Well, let's go through our laundry list of what we want out of dark matter. The first thing is we don't want it to have a large electromagnetic charge. So we don't want it to interact with sort of order 1 strength with the photon. Otherwise we would see it, right? It wouldn't be dark. It would be emitting light at us, and it wouldn't be called dark matter, it would be called bright matter. So that rules out a large number of players in the game. All of the quarks are out. The photon is massless, so it wouldn't have been able to make it up anyway because it's radiation, it's not matter. The leptons, the electron, the muon, and the tau, they can't make it up either. And nor can the W boson, which also has an electromagnetic charge. Okay, but you still have 6 players in the game. Why not one of those guys? Well, you can't have it interacting strongly with the strong force either. So this tells you it can't be that gluon particle I told you about earlier, nor can it be the quarks, which had already been ruled out anyway, but now they're doubly ruled out. It definitely can't be one of those. Okay, so 5 particles left. Surely one of these might do it. Well, they need to have enough mass, right? To make up 27% of the energy in the universe, they have to be pretty heavy. And from observation, we know that the heaviest neutrino is very, very light. So, sorry, no dice, not one of the neutrinos either. So that leaves 2 particles, the Z, which is involved with the weak nuclear force, and the Higgs boson. But there's another requirement on dark matter, which is that it has to be stable, right? It has to still exist now. If it were produced in the early universe, it has to have survived billions upon billions of years to still be here today. And we know it's still here today because some of the evidence that I showed you from previous slides is evidence from now, not evidence from the cosmic microwave background, which was so long ago. So it has to have been stable, or at least very stable on the order of the lifetime of the universe. So it's not the Higgs or the Z either, because these decay extremely rapidly. In fact, the way that we observe these at colliders is through their decays. We don't observe the Higgs itself, we observe what it decays into. We don't observe the Z boson itself, we observe what it decays into when it's produced. So none of the particles in the standard model work. We need new physics. So that's where I come in, what we call beyond the standard model theorist. So I try to go beyond these particles and postulate new ones which could make up the dark matter and solve all of your problems. Slight exaggeration. So that's where one of these other sort of philosophical questions comes in, which I was alluding to earlier, which is where are we going? Right, so where are we going with all this as theorists? Not to get into too deep, where are we going as humanity as a whole? So the first question you might ask is, okay, well, how did dark matter come to be? I gave you lots of different examples of evidence of dark matter. I told you that it might have been created at the end of the cosmic inflation period. I told you that it could have had an important impact at various different stages in the evolution of the universe. So you want to cook up a story of how dark matter came to exist that complies with all of that experimental evidence. So one idea, which I will name in just a couple of seconds, is the following. The dark matter was produced at the end of inflation. It sort of reached the thermal equilibrium with the standard model. So the standard model and the dark matter was just interacting with each other all the time. Exchanges were going dark matter to standard model back to dark matter, and they were in equilibrium. And as the universe expands, the amount of dark matter, so here on the y-axis I have shown abundance, the amount of dark matter starts to drop, because as the universe expands, it cools down, so the amount of energy stored in it, in the dark matter, decreases, because its temperature is decreasing. And since energy is related to temperature, if the temperature goes down, the amount of energy goes down. The amount of energy is synonymous with the abundance, ergo, it goes down as the universe expands. But eventually, the universe expands so much that the interactions no longer go both ways. The dark matter can no longer find other dark matter to annihilate into standard model particles, and so the process no longer happens the way that you do, and the annihilation rate fixes the final abundance of dark matter when the expansion has got too fast. And depending on the size of the interactions, you can either freeze out with an abundance here or one of these two down here. depending on the interaction strength that dark matter has with us, which is one of the sort of unknowns that we would like to understand, is how strongly does dark matter interact with us. Well, one thing that we do know is that the annihilation rate, if this is the story, has to have a particular value, roughly speaking, at the order of magnitude level, because otherwise it wouldn't give the final, what we call the relic abundance of dark matter that we observe, that we know from the cosmic microwave background. So we at least know that the product of this interaction has to have been of a certain size at the time when the dark matter was formed, if it follows this story, which we call freeze out, because it was warm and eventually it froze out. Another nice story that we like to tell is that dark matter was not produced in the early universe, but instead it sort of gets leaked by the Standard Model. So all of the energy in the early universe was contained in Standard Model particles, which were slowly sort of dumping a little bit of that energy into dark matter particles. So this would require a very small interaction, but non-zero interaction with dark matter particles. And so the arrow is only pointing in the Standard Model to dark matter direction. So as that energy gets leaked into dark matter, the abundance goes up with time, and eventually it stops going up when the mass and the temperature, the mass of the particle that's doing the leaking and the temperature at which you are, because remember time and temperature are equivalent, reach the same value. And so the temperature is roughly m chi, and so when mf is m chi, this stops happening, and m chi is the mass of the dark matter. So at this point, you've sort of frozen in the amount of dark matter, and depending on the size of the interaction and the particle that's doing the freezing in, you can have a different final abundance and a different time at which this process stops. So this is called freeze in. So those are two of the sort of nice stories that we like to tell about how dark matter came to be. The reality of it, however, is that we as theorists have done a very good job of coming up with all sorts of different mechanisms for how dark matter could come into existence. So to sort of understand what the different mechanisms might be, it's handy to think of it as a flowchart. The first question you might ask is, okay, was dark matter ever in thermal equilibrium with the Standard Model? So remember I told you about freeze out, where the dark matter was produced in the early universe and it had the same temperature as the Standard Model particles. So that was thermal equilibrium. So depending on your answer, let's say we say yes, then you know that in the early universe, dark matter contained a certain amount of energy. So you have to ask, okay, well the dark matter is cold now, so it has to have lost a lot of that energy. It's not hot with some intrinsic temperature now, so where did its energy go? So you could postulate the existence of something called a dark sector. So other dark particles, not necessarily dark matter itself, but particles that don't interact with us, where it could have dumped all of its energy and just sort of hidden it under the rug out there. This one is relatively well constrained by observations of cosmology, and so we know that in order to satisfy this, you would have to come up with a relatively creative theory. And in particular, the era of Big Bang nuclear synthesis and the cosmic microwave background provide strong constraints on this option for where the energy sort of got dumped. So then you might say, okay, well, we dumped all of that energy in the Standard Model. So then you can ask, okay, well, did it go directly into the Standard Model like I showed you on the freeze-out slide a couple of slides ago, or did it do something a little bit more convoluted? So if it does something a little bit more convoluted, there's many different models which have fancy names like secluded dark matter, or SIMP dark matter, or elder dark matter. People love acronyms, so we come up with lots of different models where you can indirectly dump energy into the Standard Model. Or you can dump dark energy directly, and that's freeze out and its variations. Okay, so that was the dark matter was in thermal equilibrium branch of this model map. What about the other branch, where it was never in thermal equilibrium? So this was where it didn't have the same temperature as the Standard Model particles, and it wasn't interacting strongly enough to reach that temperature in the early universe. So then you have to ask, okay, well, how is it produced? So one thing you could say is, okay, I'm going to postulate that there were some initial conditions which were satisfied. So maybe the particle that did inflation, the inflaton, decayed just the right amount into dark matter, and it has no further interactions with us. Or maybe it's something like what we call an axion, which solves a different problem about standard model physics, which I'm unfortunately not going to be able to tell you about today. But that had some sort of initial angle associated with it, and it just oscillates around, and that oscillation contains some energy, so maybe that's what did it. That's another example of what you would call initial conditions. A type of dark matter candidate which has received more attention in recent couple of years due to LIGO is the possibility that it's made up of what we call primordial black holes. So if you remember, I showed you that pretty picture of the cosmic microwave background and told you about how it was anisotropic. Well, anisotropies in the early universe can lead to large overdensities, so regions where there is much more matter than you normally would have expected in a small region. And if that reaches a certain critical value, that could have formed a black hole in that early universe stage rather than now, and so that's why we call them primordial, and that could be the dark matter. That's another example of where initial conditions set what the dark matter abundance is now, and so these are disconnected from their interactions with us, the standard model. And then there's the last one, which is we have tiny interactions with the standard model, and this is freeze-in with its variations. So in terms of theory mixing in with experiment, you might ask, okay, well, which ones of these can we test experimentally? Which ones can we rule out, or which ones can we hope to someday observe? So these all have a large experimental program associated with them, the ones where initial conditions set the relic abundance. Right? Primordial black holes can be constrained either using LIGO itself or using measurements of lensing in different astronomical systems. These ones, axion and ALPS. ALPS is sort of a variation on the axion. There's a very rich dark matter experimental community looking for these guys, so hopefully they will come up with something. But if they don't, you can also hope to look for freeze-in and its variations, and in fact, I will tell you a little bit more about that in just a moment. Freeze-out, you can also test in many different ways. Secluded, SIMP, elder, you can also test those. This one is maybe the one where it's a little bit more difficult to test, just because it could just have no interactions with us whatsoever, and so then, well, good luck. So, in a sense, you can think of dark matter and the theory landscape as being a many-headed hydra, right? Where you kill one head, 10 pop up in its place. You try to do your best to reduce the number of theories, but the number of theories just proliferates. So the hydra is the number of theories, and you can think of one of these guys as an experimentalist or an experiment trying to kill one of these models. But we as theorists also like to have fun sort of killing off these models, telling people, oh, well, actually that one's not going to work due to some evidence that people hadn't considered previously. So this is part of what my work as a theorist is composed of, which is we want to discover more models. So, for example, here's the title of a paper I wrote with some collaborators a couple of years ago, where we said, okay, one of the models that people thought was a good one is maybe not such a good one. So that's an example of theorists killing off heads as opposed to producing them. But at the same time, we produced more heads, so really it's one and the same. And indeed, we produced more heads in a second follow-up paper. But we're also interested in uncovering new ways of testing these models, right? So you don't want to just make models and then say, okay, well, good luck testing them, each one is as good as the other. You want to see if there are other ways of testing these dark matter models. So that's why in these last few slides, I would like to tell you about the theorist's current work. And this is related to the idea that dark matter might be charged. So you're going to say, well, hang on a minute. 15 slides ago or so, you said dark matter can't be charged. Now you're telling me it can be charged? Well, in the freeze-in story that I told you, you could have very small interactions with electromagnetism, and it was electrons and positrons which were annihilating in the early universe to produce via that photon, that mediator of the electromagnetic force, some charged dark matter particles, here denoted as chi plus and chi minus. But just that charge is really, really, really small. Way, way smaller than the electric charge of an electron or a positron. And so this is sort of the region of territory that we would be interested in here, which I will explain what all of these curves are in just a moment. And this is the line where you get the correct relic abundance via this mechanism of freeze-in. So you might ask, okay, well, how do you detect charged dark matter? Well, if it's charged, that means it interacts via electromagnetism. So that would mean that if I were to stick a really strong magnet in the room where dark matter was sitting, which it is because it's everywhere, then dark matter flowing into that magnetic field with some velocity written here of v chi would be bent. And in particular here, if you recall your right-hand rule, it's going to be bent into the page. So that's what's shown here. If the dark matter particle with the opposite charge coming in, it would be bent out of the page, and so on. Sorry. The other thing you could do is set up a big parallel plate capacitor with a huge electric field across it. If you did this and dark matter flowed into the region where you had this big electric field, the plus and minus particles go in, they get bent, and they flow out. And so what this produces is a separation of the charges. Now, as good physicists, you will know that if you have a separation of charges, that means that you're inducing two things. One, an electric field out here due to the fact that your plus and minus, your plasma out here is no longer neutral. It's got some net charge associated with it. And also, you're going to have some current flowing between these 2 points due to the fact that those particles want to come back together. And because they have some velocity in the vertical direction here, and that charge is flowing up the page. So that brings us to this concept that we are working on currently of what we call direct deflection of dark matter, which is a play on the usual experimental technique known as direct detection of dark matter. So here, dark matter comes in with some velocity, which I would be very happy to answer later some questions about how I know that it has a particular velocity and how I know which direction it's pointed. So please ask me that later. But it comes in and it reaches this region of very large electromagnetic field, which is oscillating. And this produces little oscillating millicurrents in the wake of that deflector, as well as regions of overdensity of charges, setting up that electric and that magnetic field in the wake. And you can detect this by using a resonator or some sort of cavity, for example, that you would have on the right-hand side in this shield that I have depicted in gray to make sure that no stray fields are entering the region of your detection. And you can hope to measure these tiny induced magnetic and electric fields and therefore get at the region of parameter space that I showed you a couple of slides ago. So let me build up that parameter space that I showed you. So recall that I showed you this plot with the electric charge here. Notice how small it is. The top of this plot is 1 part in 10 to the 7 of the charge of an electron, and the bottom is 1 part in 10 to the 18, so really, really small. And also, the masses that I'm talking about are really tiny. So in grams, the upper end of this plot is 10 to the minus 25 grams, and the bottom end of that plot is 10 to the minus 34 grams. This is way, way lighter than even a proton, way, way lighter than indeed an electron. So the correct abundance of dark matter is obtained on this line here. And if that were the whole story, that would be nice, but unfortunately it's not. There are constraints. The first constraint actually comes from the observation of a supernova 22 years ago, which deposited a handful of neutrinos in detectors here on Earth. And just from those handful of neutrinos, we know something about the way supernovae work and the way supernovae expel energy in that extremely violent process. And that actually enables us to place a constraint on this region of parameter space. Otherwise, the supernova would have been different than what we observed. So that's the first constraint. A somewhat similar constraint comes from the fact that we observe stars of a certain age, and indeed sometimes that we observe stars at all. This tells us something about the rate at which stars cool down, the rate at which they lose energy over time. And if you take that into account, you can place additional constraints. So bear in mind, this is again the work of theorists who are taking experimental data which a priori you might not have thought was related to the question of dark matter, and finding that indeed it is, and thereby attempting to kill some of those hydra heads that I showed you earlier. So that starts eating into the region that you might have been interested in. Then the other thing you can do is what I referred to earlier as direct detection experiments. So this is Xenon 10, which is an experiment looking for dark matter that goes into the detector, hits a particle in the detector, thereby depositing a small amount of energy, and it measures that small amount of energy and says, okay, if I see that energy, that means a dark matter particle hit one of my detector particles. Its non-observation of that deposited energy allows you to place an additional constraint on the dark matter parameter space. So that's the current status of direct detection of dark matter. What about the future status of direct detection of dark matter? So here are two curves, one for sort of a near future experiment, and here for the far future experiment. So this direct deflection dark matter experiment that I am proposing covers that. So this line and above would be entirely covered by the direct deflection of dark matter experiment that we are proposing. So that what basically brings me to my conclusion of this talk on deciphering dark matter, and indeed on what myself as a physicist I do day to day. But let me finish with a few concluding remarks about what it takes to decipher dark matter and what we do. So the first thing is obvious. We should pursue many avenues simultaneously. You should never sort of marry yourself to any one particular idea, because there are so many to be had. And there are so many experimental ideas to be had. So this not only motivates the development of new theories, but it also motivates many experimental strategies. And it's only through that symbiotic relationship between theorists and experimentalists that we can really attack that hydra together. And among the many experimental strategies, there are very different approaches. So one would be, for example, the one that I showed you here today, which is a small-scale experiment that could potentially attack a lot of the parameter space. But it also requires thinking big and going to really large-scale experiments. So here, recall that I showed you the LHC on one of the earlier slides. There is a proposal for what is currently being called the FCC, which would be 4 times larger in circumference and collide at much, much higher energies to try and probe ever smaller in those length scales that I was telling you about right at the very beginning. And both of these approaches are required to help theorists and help experimentalists eventually decipher both the nature of dark matter and other problems in the standard model, which I didn't get to tell you about. But that concludes what I have to say for today, so thank you for your attention.
Questions? Yes.
I have a question. I kind of saw this because I looked over the periodic table. But would it be possible to ever create like synthetic particles that aren't real and or like aren't already there and just like move around?
So that's a very good question. In fact, we do that all the time. So, for example, at the Large Hadron Collider, when you collide particles, you're taking ones that we know because we made them there. We took them, in fact, from hydrogen, right? So in order to collide protons, you strip the electrons off of hydrogen, you collide those guys. When you collide them, you produce a whole bunch of particles that weren't necessarily in the proton when it was collided. Instead, you sort of produce them from the energy that came from that collision, right? So if you give the proton way more energy than it has enough energy associated with it to produce new particles. And so that's, for example, how we discovered the Higgs boson. That's how we discovered the W and Z bosons, is through sort of colliding known particles to try and produce these particles that we think should be there, and then we can observe them. So yeah, we do create synthetic particles in that sense basically all the time.
Thank you.
Well, you wanted to answer this question you said in your talk, so how do you know like whether the dark matter is going in a certain direction?
Very good. So remember that I showed you the slide on rotation curves as one of the pieces of evidence that dark matter existed. And remember I also told you about the virial theorem. So that related the kinetic energy of a gravitationally bound system to the potential energy in that system. So through those two things, we know, given the mass of a particular galaxy, what we call the virial velocity of the contents of that galaxy is, using the virial theorem. So we know that dark matter has a particular virial velocity from the fact that it is bound in our galaxy. So that's how we know that it has a velocity. But that doesn't tell you anything about the direction, right? So that virial velocity is in every direction, right? And it's basically the same in every given direction. It's what you would call isotropic and homogeneous to a large extent. But our motion, relative to the galaxy, is not, right? We are on a spiral arm of the Milky Way, and we rotate with respect to some axis of the spherical halo of dark matter. So we actually have a relative motion to the dark matter. So it's sort of a misnomer to say that dark matter flows into us with a velocity. It's rather, we flow through it with a given velocity. And since we know the velocity of the sun with respect to the galaxy, we also know the velocity of us on Earth relative to the dark matter.
That was very much related to my more comment than question, which was, that reminded me of attempts to find the luminiferous ether to see this motion. What is this reference? What is this reference frame? Let me turn that into a question, because that's very much an experiment. Yeah. Can you talk about the birth of that idea of going from, hey, there might be this class of particles to sketching out an experiment with it, and how far along are those thoughts?
So yeah, that's a very good question, because that process is extremely nonlinear. So this sort of target line, so let me bring back the slide where I showed it, so people have in mind what we're looking at. So this sort of what we call a target, where you get the correct abundance of dark matter from freezing, has been known for about a decade now, from a paper by actually some researchers at Berkeley. And so we knew that this was sort of a region that might be interesting, but it's typically not accessible by usual direct detection experiments, as you can see. And so we were trying to think, okay, well, what else can you do with this region that might be interesting? And in particular, we were talking actually about these two projects over lunch one day, and we realized that if dark matter had some small charge, if you stuck a really big magnet on top of those experiments, you could kill their signal. So if they had observed dark matter, but they didn't know what it was, they didn't know for sure that it was dark matter or that it was really charged under electromagnetism, if you stuck a big magnet on top of those, then you would kill the signal, and so you would know what it was. And then we thought, oh, hang on a minute, if it does interact with electromagnetism, surely there's a better thing to do than just killing somebody else's signal. Maybe we can create our own signal. And so we went through various different iterations, but eventually we reached this one of sort of trying to deflect the dark matter. But it was a very nonlinear process. But actually, this morning we had a Skype conversation with some experimentalists in Italy who are pretty excited by it. And so once the paper is out, we'll probably shop around with different experimental groups and see who wants to build it.
Is there any cosmic process thought to currently produce a new supply of protons and neutrons?
A new supply of protons and neutrons.
And I mean, partly asked that because what happens to matter that disappears in black holes? If we have a limited supply of protons and neutrons from the Big Bang, and black holes are as ubiquitous as they seem to be,
yeah.
Where is the balance?
So that question touches on a very deep and as yet unanswered question, which is what's known as the information paradox. So it's the fact that we believe that energy is conserved, which means that you neither create nor destroy any particles, and therefore neither create nor destroy new energy. But as you say, there's lots and lots of black holes. Particles flow into black holes all the time. Where does that energy go if it's not destroyed? And so, in fact, that is the essence of the information paradox, is where does that energy go? And we know that there's Hawking radiation, but we haven't really observed, well, we haven't observed that the information that gets put into the black hole comes out in quite the same way. And so connecting those two parts together is rather difficult, and it's the source of a lot of ongoing work. But to answer your first question, protons are not really created out of nowhere. They have to be created from some energy. So if you had some excess of energy somewhere, you could create a proton-antiproton pair out of that, out of the vacuum, in fact. But you're not creating energy from nothing. You're creating energy from energy, just in a different form.
I thought that when you were talking about this charge and it being in the difference in the electric charges between the electron and the positron, can you connect that to the abundance of matter versus antimatter, the conundrum that we have of the universe being? Is that deeply connected with some people's thoughts and why there's this imbalance between matter and antimatter? Would the electric charge difference naturally fall out of something like that, or so I'm saying, is there other motivations for us to go, okay, yes, let's think about this?
Right. So the electron and positron have equal and opposite charge, but of course we all see electrons. We don't really see positrons floating about. So the answer to that question would be Nobel Prize worthy, because that's the answer to why it is that we're made up of matter and not antimatter. And indeed, that could be coupled to the question of what dark matter is. And so there is a lot of a large body of work where people have studied models where dark matter maybe has an initial asymmetry which gets transferred to the standard model. And so then you might ask, okay, well, what was the source of the initial asymmetry? We don't know. You could also have maybe some additional interactions which allow for the conditions required to make more matter than antimatter. So yeah, that's a source of a lot of ongoing work. And in fact, some of the other work that I have been doing, which is nothing that I presented here, relates that question of the baryon, what we call the baryon asymmetry of the universe, to dark matter. And there it's not dark matter itself that supplies the baryon asymmetry, but rather enables the process by which the baryon asymmetry would have been created. So that's work that I unfortunately don't have time to talk about, but is also ongoing. Yeah.
If you had to point to one point in your cosmology timeline where dark matter would have been, if its behavior would have been different, which point would it be most catastrophic?
Most catastrophic. Probably Big Bang nucleosynthesis. So it's actually interesting to ask the question, how much could you change the story while still producing enough light nuclei that stars will form the way that they do? And people do think about that quite a lot. In terms of the sensitivity to changes in the dark matter story, I think Big Bang nucleosynthesis is probably one of the areas where it's most sensitive. So if the dark matter were, like I was saying, hot during that period, or even just a little bit hot, it would change the story dramatically. And so whether that would give rise to, it might give rise to a universe. It wouldn't be this one. But whether things like the Earth would exist, I don't know the answer to.
Well, with that, let's thank our speakers.